Simulation. Inside a simulation.
We're still in
We never left the Shoney's. We haven't left. It's a trap.
Alright, let's talk GR, shall we? Let's do some of the mathy kind of stuff now. So, in GR we talk about the metric that specifies the space-time interval between events. I don't remember anymore. Which of you had me for physics 280? Yeah, but not you.
Well, no, we both had Dr. Hendrick.
You both had Dr. Hendrick and you had me. Okay, did you guys talk about space-time intervals, like the proper time and stuff like that?
We
We talked about proper time, yes.
Yeah.
I don't know if we talked about space time.
Okay, we'll see how this goes. So, okay. First of all, in just ordinary Euclidean geometry, the metric is what specifies the distance between points. So, here's a plane. We could use coordinates x and y, and we could have 2 points that are near one another. And so if we use some particular coordinate system, then they might have some coordinate differences, dx and dy, just the differences in the coordinates of the 2 points from one another. So in other words, dx is just x2 minus x1, dy is y2 minus y1. Doesn't matter which point is which, maybe that happens 1, that happens 2, but it could be the other way around. Certainly there's no reason these dx's and dy's can't be negative. So we will say that dl is the distance between those points. It's the hypotenuse of that cute little right triangle right there. What is dl squared? What's dl squared in terms of dx and dy?
Dx squared plus dy squared.
It sure is. dl squared is just dx squared plus dy squared. In this case, dx and dy don't even have to be small in Cartesian coordinates. It's as big as you like, it's just a triangle, so there's no implication that it's for a small distance between them. But in general coordinates, we do have to think in terms of the limit as the separation becomes very small, because in curvilinear coordinates, like polar coordinates, it's no longer quite a symbol, but it's not terribly complicated either. So this is for Cartesian coordinates. What if we have plane polar coordinates? So in other words, if we have, instead of using x and y, I'll still draw x and y on there. But remember, of course, in plane polar coordinates, we use r and theta to specify the coordinates of points. So here's 2 points. And I can still, in the limit as the separation becomes small, make a little right triangle. And so, again, I want to know the distance between them. I guess I can just make that solid 2. And so I can call that angle right there d theta, the small difference in in the theta value for the 2 points. And I will call the difference in the radial coordinates dr. And really dr is r2 minus r1. And as long as the points are small, I can make a little triangle like that, and that's dr. That's not quite right though, right? Because in other words, what I really have to do is make an arc from that point and figure out what the difference in the distances is. But as long as d theta is small, dr is small, I make a very small error by just dropping a perpendicular to that line as opposed to swinging an arc. And so that's why we're needing to make small coordinate differences. We're going to get a formula that's right in the limit that the distance is small between the 2 points. So there's dr. What's that? What's that distance right there? So we're sweeping through d theta, a distance. What's that? No, you're being a little more complicated than I want. It's just r d theta. It's just r d theta. Now again, this is better and better as the distance between the 2 points gets smaller and smaller. Because, you know, should I use r or should I use r plus dr? Blah, 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 blah. It doesn't matter as long as the points are very close together. So this is r d theta. So I've made a little right triangle whose sides are dr and r d theta. So, for infinitesimal separations between the points, dl squared is what in polar coordinates?
dr squared.
Mm-hmm. dr squared plus r d theta squared, which I can say is r squared times d theta squared. So that's for polar coordinates. Now, I will say that very quickly it gets tiresome to keep writing all those parentheses around the differentials, around the little d thetas, dx's, and so forth. And so, what we will typically do is just say things like dl squared is dx squared plus dy squared, or dl squared is dr squared plus r squared, d theta squared.
Is that supposed to be dx
Sure is, yes, certainly. dx squared plus dy squared, which is sloppy notation, of course, because dx squared could be interpreted as the differential of the quantity x squared. But it doesn't mean that here. It doesn't mean 2x dx. It means dx, the quantity squared. And so we just have to, unless specified otherwise, differentials to the second power mean the differential squared, as opposed to d of x squared is dx squared. Because otherwise you just keep writing all these parentheses, you're just getting tiresome, you know what we mean. Okay? So, this formula, or this formula, is a specification of what we call the metric, the distance measure in the plane, in the Cartesian, or in the Euclidean plane. And not every plane has a natural distance measure. So, for example, is there any meaning really to how far apart those 2 points are on the HR diagram? Not really, right? That's not really a distance. Of course, you could get out a ruler and measure it, but there's nothing intrinsic about there being a literal distance between points that have coordinates that are luminosity and temperature. Those are not intrinsically something that represent displacements, for example. And so this is an example of a so-called manifold, which you can think of as being like a I mean, there's a specific definition of what a differentiable manifold is, but just think of it as like a continuous space of points. This is a manifold that doesn't have a natural distance metric on it, doesn't have a natural metric on it. But the plane, Euclidean plane, does. There's such a thing. It's natural thing to distances between the 2 points in the plane, and so on and so forth. So, suppose I were to rotate the coordinate system. So I just swing the axes through some angle. Would the coordinates of the points change? Sure, right? If I rotate the coordinates, then the x and y coordinates for those points will change. Will the distance between them change? No. So we have to distinguish between what's intrinsic and what's not intrinsic. In other words, the coordinates of the points change. That's not an intrinsic property of the points. What their x and y coordinates are depends on our choice of axes. But the distance between them is a geometrical property of the space that they're living in. And so changing the coordinate axes doesn't change the distance. Okay? So, any questions so far? Let's look on the surface of a sphere now. What's the big difference between a plane and a sphere in terms of the geometry of their surfaces?
One's curved,
One's curved, the other's flat. That's right. So this is important. We're talking general relativity. It's supposed to be about curved space and so forth, curved space-time. We're going to specify something important that's different for intrinsically curved surfaces versus flat surfaces. So, metric on a sphere of radius r. Now that's maybe a terrible mistake. I'm not Dr. Trees. I always hear, oh, that was going pretty well there. Let's see. You know what, that could have been a lot worse. That's not too bad, as a matter of fact.
How I come out of every exam.
What's that?
How I come out of every exam. That could have been a lot worse.
That could have been a lot worse. That's right.
I can't see my drawings doing as well as yours.
So if we use polar coordinates on the surface of the sphere, theta and phi, then if r is the radius of the sphere, because this is sphere radius r, so what I've done there is I've drawn a little patch on the sphere that is d theta in angular width by d phi in angular width. So it's a little rectangular patch on the surface of the sphere that spans d theta and d phi in the two angles that we can use to specify locations on the sphere. So what is that distance right there? In other words, we want to find the length of the sides. That one's already theta. Yeah, that one's already theta. And what about this one? So remember there, this is the one where we could go like, okay, here's like a circle that goes around the axis. And so the radius of the circle isn't r, it's r sine theta. Yeah, it's r times the sine of theta, because theta is the polar angle there. So r sine theta is the radius of the circle of which that sine is a little arc.
R sine theta times dp.
R sine theta d phi, right? It's sweeping angle d phi on a circle of radius r sine theta. So that's r sine theta d phi. So suppose, now we've often, before when I've done spherical coordinates with you or with other people, what you'll do is say, what's the area of the patch? Well, it's r d theta times r sine theta d phi. So the area of that little patch is r squared sine theta d phi. But we could also say, what's the distance between those two corner points on the patch, which differ in their coordinates by d theta and d phi on the sphere of radius r. So in other words, we're once again saying that we're making a little right triangle whose hypotenuse is the distance along the sphere between those 2 points.
So it's dl squared is those two planes squared.
Yeah, it's dl squared is the sum of the squares of the 2 sides. So it's r squared d theta squared plus r squared sine squared theta d phi squared. So here's the thing. On a plane, we can use polar coordinates, but it's possible to find Cartesian coordinates. In other words, it is possible to find a coordinate system where everywhere on the plane, the metric takes this particularly simple form, that everywhere dl squared is just the sum of the squares of the coordinate differentials. Turns out that's impossible to do on the surface of the sphere. You cannot find a Cartesian coordinate system that covers the surface of the sphere. In other words, while you can produce what's called a local Cartesian coordinate system, you can't find a global Cartesian coordinate system. There is no choice of coordinates where the metric on the surface of the sphere in those coordinates is everywhere dl squared equals dx squared plus dy squared. So here's our assertion. We're not proving it, but intuitively it makes sense. Because if you think about it, if you could do that, you could wrap a bowling ball with a piece of paper and not have it crumble up on you. Because the piece of paper has Cartesian coordinates. You could put Cartesian coordinates on the piece of paper that specifies the distances between all the points. If you could smoothly wrap that piece of paper and entirely cover the surface of the sphere, you would then have produced a Cartesian coordinate system, or a coordinate system that covers the surface of the sphere and properly specifies the distances between all the points. But in fact, you cannot wrap a bowling ball with a single piece of wrapping paper. It will always crumple up on you if you try to do that. And mathematically, that's equivalent to the fact that you cannot cover the surface of a sphere with a single Cartesian coordinate system. It is impossible to find a Cartesian coordinate system that covers an entire sphere. In other words, i.e., there do not exist coordinates x, y, such that equal to dx squared plus dy squared everywhere on the sphere. Can't be done. Now in my notes that you could download, I use xi and eta, which is a traditional choice in general relativity, is using xi and eta for kind of generic coordinates. But the problem is, xi is this freaking letter, which takes a lot of practice to get any good at all at writing. So I'm just going to call it x and y. This is equivalent to saying that a sphere possesses what we call intrinsic curvature. Sphere exhibits intrinsic curvature by its very nature. A practical application is that you cannot wrap a bowling ball with a single sheet of wrapping paper and not crumple it up. Can't do it, can't be done. Kind of a similar theorem which says that you can't cover a sphere with fibers, with hair, and not have a whorl in there somewhere. And if you think about it, that's true too. In other words, our heads, we've got this in the back of our heads. It's an application of the fact that you cannot cover a sphere with hair and not have it whirl somewhere. Just try to imagine doing it. It can't be done. There's going to be a place where there's a whirl in the hair. Because, here I am, I'm covering. Whoops, I made a whirl up here. Maybe if I curve, no matter what you do, you can't do it. There's always going to be a whirl. If you put hair everywhere on the surface of the sphere, there has to be at least one whirl in it, so to speak. Now, what about a cylinder? Can you cover the surface of a cylinder with a Cartesian coordinate system? The answer is yes. How could you do it?
Piece of paper.
You got it. Yeah, take a piece of graph paper, literally wrap it around a sphere, and you will have a Cartesian coordinate system because the distances between the points on that graph paper is exactly the same as when it was flat, and you don't crinkle or crumple it anywhere. You can just smoothly wrap it around. And so a cylinder has what we call extrinsic curvature.
So does that imply that we have to wrap it around only the sides and not the lids?
Yeah, we're not wrapping the lids here. Yeah, we're just wrapping the cylinder itself. Yeah. So just the cylinder itself as opposed to the lid itself. A cylinder, and I really mean an infinite cylinder here. A cylinder exhibits extrinsic curvature. A piece of graph paper can be rolled into a cylinder without stretching or tearing it. And so the graph paper will constitute, the lines on the graph paper will be a Cartesian coordinate system on the cylinder. It's a cyclic coordinate system. In other words, one of the axes repeats itself because of the fact that it circles around, but that doesn't change the fact that you've got a coordinate system where everywhere dl squared is dx squared plus dy squared. The exception is along where the seam is, where the coordinate repeats itself that you've wrapped around. Strictly speaking, if you jump across that line on the surface, you get a big change in the coordinate, right? In other words, if you've wrapped it around and the x-axis is the one wrapped around, there's x equals 0, and let's say the circumference is 1 meter, there's x equals 1 meter. 2 points very close together have a very large change in their coordinates. But that's just an artifact of your arbitrary choice of where you chose x to be 0, and so it's not really an intrinsic property of the surface itself. That's just a technical detail of the choice of coordinate system. A piece of graph paper can be rolled into a cylinder without stretching or tearing it. Now you're probably starting to wonder, what is the point of this? Trust me, that this does connect with relativity and all that, but for now we're just having some fun with geometry, but we'll make the connection soon enough. So I can't wrap an entire bowling ball with a piece of paper. Can I glue a small piece of paper to the surface of the bowling ball without having any significant crumbling up of it? Very small. Yeah, a very small piece, right? If I have this, if I have a sphere here, I could tear off a little square of paper and, what's it supposed to touch my tongue? Anyway. Awkward.
Individual flat spheres.
Okay, note to self, be more careful next time for that. Okay, anyway, I can tear a little piece off and I can stick it on a piece of paper. And if you think about it, if that little square, I stick it on the surface of the bowling ball or whatever. If you think about it, that little square could have a little grid on it, part of the Cartesian coordinate system. And so in that little region of the sphere where I glued that little piece of paper, I've got what we call a local Cartesian coordinate system. To an awfully good approximation in that little area, I've got a situation where dl squared is dx squared plus dy squared. So I can't do it for the whole sphere, but what I can do is paste lots and lots of little local Cartesian coordinate systems from little torn up pieces of graph paper over the surface of the sphere. Okay, does that make sense? In fact, if you think of us as, if Earth was a perfect cue ball, and take the floor here, okay? I couldn't tile the entire surface of a giant cue ball Earth with tiles smoothly. In other words, the pattern would have to be disrupted. I couldn't make a nice Cartesian pattern like this everywhere on the surface of the Earth. On the other hand, for something the size of this room, which is much smaller than the radius of curvature of the Earth, here's an awfully good approximation on the floor to a locally Cartesian coordinate system on the surface of our perfect cue ball spherical Earth, if you like. Giant cue ball spherical Earth. So, what do we say? We say a local Cartesian coordinate system can be constructed in the vicinity of any given point on the sphere. And pooling a little piece of paper is a way to think of it, but more typically what we do is we think of what we call the tangent plane. In other words, if I take a sphere and take a plane and make it tangent to the surface of the sphere, and then imagine that the tangent plane is a transparency with graph paper printed onto it. And I shine a light perpendicular to that piece of graph paper pointing right at the center of the sphere, and I look at the shadows cast by that Cartesian grid on that transparency. Then I will set up a grid which distorts away from the point of contact. The further away you are from the point of contact, the more distorted the grid is. But near the point of contact, it looks like a little Cartesian coordinate system on the surface of the sphere. So the formally mathematical way you do construct a local Cartesian coordinate system is this projection using the tangent plane to the surface of the sphere. So a local Cartesian coordinate system can be constructed in the vicinity of any given point on the sphere by projecting a Cartesian coordinate grid down onto the sphere from the tangent plane through the point in question. So by projecting a Cartesian grid on the tangent plane, that touches that point, down onto the surface of the sphere. Say the grid lines distort as we move away from the point P at which we are constructing these coordinates. The metric in those coordinates will be dl squared equals, we'll call them x and y again, dx squared plus dy squared, but there will have to be corrections, plus higher order terms that go to 0 at P. So the closer you are to P, the more nearly correct it is to say that dl squared is just dx squared plus dy squared. It's not perfect, but the closer you get to point P, the closer it is true to being that that is the correct distance between the points. So now we're ready to start connecting this to relativity. So in special, oh, I'll slow down because there's still writing happening here. Any questions? So the analogy, I'll just say it in words first. The analogy that is to be made here is that while a sphere is curved, in the vicinity of any point on the surface of the sphere, it looks flat, right? If you are considering a small enough region, it's approximately flat. You can put a local Cartesian coordinate system on it that almost gives the right distance between points. Do you notice the curvature of Earth's surface in an everyday basis and don't even?
Well, this is just like the one main reason for flat Earth.
Right, yes. Yeah.
It looks flat.
It looks flat. If it looks like a duck and quacks like an elephant, it must be a duck. It's basically the argument that they make. Anyway, far away from any stars and planets where gravity is very weak, space-time is flat. We talk about flat space-time. Special relativity describes flat space-time. In a gravitational field, if you consider any region small enough, then you can construct coordinates where the space-time interval is almost correctly given by the special relativity flat space-time metric in those coordinates, but you can't cover all of a curved space-time with such a coordinate system because the space-time is intrinsically curved because that's what gravity is, essentially, and there's a gravitational field there. And our freely falling frames in the principle of equivalence, where if the region of space-time is small enough in space and time that the gravity can be considered uniform within it, then you can construct a coordinate system that is locally flat, looks like special relativity, meaning that things with no force on them move in straight lines at constant speed and all that sort of goodness. So this will become clearer as we go along, but that's the idea, is that these freely falling compartments are the equivalent of constructing little rectangles on the surface of a sphere that are almost little flat surfaces. Believe it or not. And that was Einstein's big insight, that you could make that analogy. So, in special relativity, the Minkowski metric, it was Minkowski who had the insight to geometrize special relativity, if you will. The Minkowski metric is ds squared is c squared dt squared minus dx squared minus dy squared minus dz squared when expressed in Cartesian spatial coordinates. When expressed using spatial Cartesian coordinates. Cartesian spatial coordinates is available. You never know whether to spell spatial with a T or a C. So I find it hard to draw in 4 dimensions. I find it even hard to draw in 3 dimensions. So let's do the usual thing of pretending space has 1 dimension. We're in a world where everything moves along a line and evolves in time. So no matter who you took special relativity with, I know you did space-time diagrams. So remember that in a space-time diagram, that time goes up, right? So there's the t-axis, there's the x-axis, and we talk about world lines and so forth. We're going to use natural units most of the time because they simplify writing. So in natural units, c by definition is equal to 1. Did you guys, who took Dr. Andrew, did you guys ever do that? Just set c equal to 1?
I think so.
Yeah. One way to do that is to say, I'm going to measure time in meters, where a meter of time is how long it takes light to travel 1 meter of distance. So then the speed of light is 1 meter of distance per 1 meter of time. That's not cheating, it's perfectly fine. There's no reason not to choose the unit of time to be how long it takes light to travel 1 meter. It's not artificial at all. Get over it. Another way to do it is to use light seconds as your distance unit. Call a second of distance the distance that light travels in 1 second. And that works too. You can make your distance unit be the light second, but then just call it the second of distance. Use the same units to measure distances and times. Either way, the speed of light is 1 in those units. It's dimensions because you're using the same units for distances and times. So I'm going to cheat and just keep reusing my diagram. You might want to keep making new axes. It's up to you. What does the world line of a photon look like in natural units? How does it travel? It's a 45-degree angle, right? It's a 45-degree angle because it's covering equal amounts of distance in equal amounts of time. If you use units where the speed of light is 1, then you want delta x over delta t to be 1 for light rays. So if here is some event p in space-time, then there are two, Yeah, you know what I mean. There's 2 photon light rays going through point P, through event P. What do you call that? Crisscross light rays going through event P. That's the through P. The light cone through P. Is that, you guys talk about light cones at all? Looking like light cone is not familiar. Maybe, or maybe you just forgot, right? Yeah, the light cone. The reason we call it a light cone is if you did this in 2 dimensions, if you had 2 dimensions of space, x, y, t, the light cone literally is a cone if your space is 2-dimensional in your space-time. It's literally a cone because the light rays are making a 45-degree angle no matter which way they go through event P. So we call it the light cone because with a 2-dimensional space, it's literally a conical surface in the space-time diagram. I lied, I'm just going to keep drawing new pictures. There's 2 events, P and Q, in space-time. Slant it a little more. Actually, for now, just let it be delta x and delta t between, in other words, there's a time interval delta t between those events and a distance interval delta x between those events.
Is that
It is. Thank you. So, when we talk about the space-time interval between the events, what we said is that it was ds squared is c squared dt squared minus dx squared minus dy squared minus dz squared. We could put in deltas, delta c squared, blah, 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 blah. So, in natural units, the c goes away, and then it looks nice and symmetric. And so, in fact, all of special relativity can be essentially derived from the following postulate, that all observers agree on the value of ds squared. If you have observers in relative motion so that the events have different coordinates, different t values, different x values, different y values in the 2 frames, any observers who construct this quantity using their coordinate system will come up with the same number for ds squared. So that this so-called space-time interval between events is an intrinsic property of space-time and not dependent on the coordinate system. Time dilation, constancy of the speed of light, and all that follows from the assertion that everybody agrees on the interval. Question?
Is that because essentially the dx, dy, dz is always going to be equal to dl squared, and no matter what coordinate you have, it always equals dl squared?
So for photons, this quantity will be 0 because the light travels a distance c dt in going between the 2 events, and so c dt, c squared dt squared, the distance that the light travels between the events, is equal to the distance between the 2 events. And so when you subtract, you get 0. So if everybody agrees that if one observer gets 0 for a photon, every observer gets 0, then no matter what coordinate system you use, you're concluding that the speed of light is the same. That, in other words, if you take dx squared plus dy squared plus dz squared divided by dt squared, it'll be c squared. Everybody will agree on that. So if everybody agrees on ds squared, they agree on the speed of light automatically. It's built in to that being the quote-unquote distance measure of relativity. Time for the break, so we'll